Oh, before we started, I did this the other day. I just now remembered. So the surface that we talked about, or that we were working with, we found the surface area of in our example. And I thought it might be a cylinder, and then I thought I was wrong, and we talked. Several of us talked about it afterwards, and I think we figured out what it looked like. But I graphed it in Mathematica so we could see for sure what that surface was.
Just like the one that.
There we go. So it turned out to be a paraboloid. So our parametric surface was square root of u cosine b, square root of u sine b, and u. Z was u. So the square root of u gives us the parabolic shape on the sides. The cosine b and sine b gives us the circle, and then u goes from 0 to 4. So that turned out to be a paraboloid. And then there was one, they had the graph in the back of your book for problem number, was it 51? Which was a little bit different. It was a spiral ramp. So that was this one. So I graphed that one just because I thought it was interesting. And this one was different because we had u cosine b for the I component, u sine b for the j component, but z was 2b this time rather than u. So that's why we end up with the spiral shape. So for any particular angle, our radius goes from 0 to, what does it go to? 0 to 3. So for any particular angle, we get the whole radius. We get that spiral. And then if we look at it straight on, we end up with a circle projected down onto the xy plane. All right. Now we're ready for 15.6. I'm going to talk about surface integrals on scalar fields. And then tomorrow we'll talk about surface integrals on vector fields. So let me do this really quickly. All right, so just to kind of recap what we did in the previous section in 15.5. So if we had a parametric surface, we have our surface represented by parametric equations. Tick, yeah. We have R, if we had a parametric surface, R of u and v. We decided that a normal vector to the surface our normal vector was R sub u cross R sub v. So that was a normal vector, and our surface area, little increment of surface area, so our surface area element, I'll call it, ds, was the magnitude of Ru cross Rv, R sub u cross R sub v, times du dv. So that was the area of a little tiny piece of surface on our parametric surface. And the surface area, we just summed these over the area, or over the surface, was the double integral over our region of this quantity. And R is our region in the UV plane. Now think back to what we did a couple of sections ago when we defined our line integral. So we defined our line integral for a scalar function. We integrated over our curve, f of xy ds. And we said we evaluated that by evaluating from a to b. We expressed our function in terms of our parameterized curve, f of r of t times the magnitude of r prime dt. So we parameterized our curve in terms of t, we expressed f in terms of the parameter, and this is how we evaluated this line integral. So, and we interpreted this as summing the value of f times a small element of length along our curve. And one interpretation we gave to that was if f was a density function, we could find the mass of a wire in the shape of our curve. So that was one interpretation we gave to a line integral. The other interpretation, we could think of f of xy as a height above the plane, and our curve is a curve in the plane, and then the line integral would be the area between the plane and the height function. So the area of the fence along that curve is the way I described it. We're going to do something similar with surface integrals. We have this integral, this double integral that gives us our surface area. We're interested in summing some function times a small increment of area on our surface. So what we're going to do for a surface integral what we want to do is we sum the value of some function f of x, y, z times the small area ds. And we sum that over the surface. That's what we're going to call a surface integral on a scalar field. So we're going to define our surface integral. As the double integral over our surface of f of x, y, z ds. And we're going to, the other way we can express this is if we have our surface expressed parametrically, this is going to be the double integral over r of f of r of u and v. So we express our function in terms of the parameters times the magnitude of r sub u cross r sub v du dv. So f is our function expressed in terms of the parameters that we use to parameterize our surface, and this is the magnitude of our normal vector, and our region r is the region in the UV plane. So this is exactly how we defined our line integral. We're using the same thinking. We're just extending this to a surface integral. So one way we could interpret this, and there are a few problems that we'll do that interpret it this way, is now if f of x, y, z is a density function per unit area, and we're finding the mass of some material that's in the shape of this parametric surface. So we're multiplying the density at a particular point times a tiny area of that point, and we're summing over the surface. That's one interpretation we could give to a surface integral. And if the way that we're normally going to work with these is if z is some function of x and y, ds is this familiar quantity that we've been working with, is f sub x squared plus f sub y squared plus 1 dy dx. And we would express f of x, y, z is f of x, y, f of x, y, and I'll make this capital F. So we can express, we can come up with a function of x, y, z by writing capital F as f of x, y, and f of x, y. And this should be a capital F also. And then R would be our region in the xy plane. So normally we're going to be, for the most part, we're going to work with functions expressed in terms of x and y. And we would work with these quantities in our surface integrals. So questions on our definition of a surface integral for a scalar function. So we have the same kind of idea that we talked about with line integrals, just extending it to a surface. So what I want to do now is just work through a few examples of surface integrals. So what are we thinking over there?
Definitely clock. Yeah, and then it's uncurling, and then it'll curl again. But how does it get down to like this stuff? Like,
You have to keep watching. You have to come
it's
back.
Different block for you.
Yeah, you have to come back here several times today and see what it looks like.
You get a hold of their hour. Just randomly coming across.
All right. So let's work through a few examples with surface integrals, and then what we're going to do tomorrow is we will do surface integrals with a vector field. So rather than the scalar function, we'll have a vector function, and we'll talk about how we're going to do a surface integral with a vector function. We'll talk about flux and what a flux integral is. But for today, for the first one, we want to evaluate the surface integral of x minus 2y plus z ds, where s is z equals 15 minus 2x plus 3y. And we have 0 less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 4. So let's before we start working, let's think about what we're working with. First off, what is this surface? What is it called? A plane. And these boundaries, what is our region in the xy plane? 0 to 2, 0 to 4. So what shape does that give us in the xy plane? A rectangle. We have a rectangle in the xy plane, so we're projecting that rectangle up onto this plane, and we're evaluating this function over that surface. We're evaluating the integral of this function over that surface. So we could think of this function as the density function if we wanted to, and we could think of this as the mass of the plane in that region. All right, so here we have z is some function of x and y. So z equals g of xy. So we need for our ds, for our little element of area, we need our partial derivatives. So g sub x, nice and easy. Negative 2. G sub y is 3. And ds, our little area element, is the square root of, I'll write it out, negative 2 squared plus 3 squared plus 1. And our little area, that increment of area on our surface is just the square root of 14, dx dy or dy dx. And our function that we're evaluating, if we call this f of x, y, z, is x minus 2y plus z. We need to write that in terms of how we parameterized our surface. So we're going to substitute z equals 15 minus 2x plus 3y for our function there. So we can express our function in terms of our parameters on our surface. So f is going to be x minus 2y plus 15 minus 2x plus 3y. And this, if we simplify this, we get minus x plus y plus 15. And now we're ready to evaluate our integral. So we have the integral from 0 to, integral from 0 to 4 of minus x plus y plus 15 dy dx. Nice easy integral to evaluate. Nothing too hard here. When we evaluate this comes out to be 128 square root 14. Oh, did I forget to put that in here? Yes, I forgot to write my square root of 14 in. So we expressed our function in terms of our parameters for our surface, found our surface area increment, found our ds, and evaluated the integral over the region in the xy plane. So questions on that one? For surface integrals, where students usually make mistakes is one, in the parameterization, being clear about the parameterization of the surface, and two, expressing our function in terms of the parameters of our surface. Those are the two places where people usually make mistakes on surface integrals. All right, let's look at a parametric surface rather than a surface in rectangular coordinates. So we want to evaluate the double integral f of x, y ds. So we're evaluating the surface integral where f of x, y is x plus y, and our surface is a parametric surface, r of u and v. 2 cosine u I hat plus 2 sine u j hat plus v k hat. 0 less than or equal to u less than or equal to pi over 2, and 0 less than or equal to v less than or equal to 2. Let me do this real quick.
Yeah.
Are we sure at the clock now?
Okay.
My wife got a catalog from a company, it's called Uncommon Goods, and it was in there, and the one that was in there was small, this big. So I found the website of the people that make it, and they have a bigger one. It's actually from Israel. All right. So here's our function. Here's our surface, our parameterized in terms of u and v. What kind of surface are we looking at here? What is this thing? Cylinder. I think this one's a cylinder. So we just have a circle in the xy plane, and v just increases. So we're going up the z-axis. All right. So we have our surface parameterized. We have our function. So what are we going to need to do to evaluate the surface integral? We need r sub u cross r sub v. So let's find r sub u. R sub u is going to be what? Minus 2 sine u I hat plus 2 cosine u j hat. And we get no k component. What's that? This is a v. So we're doing r sub u, and this is a v. All right, and then r sub v is just k hat. We don't get any components from the I and the j. So now we need to form our cross product. So r sub u cross r sub v. I'll write out my determinant, j, k, minus 2 sine u, 2 cosine u, 0, and 0, 0, 1. When we form this cross product, this comes out to be 2 cosine u I plus 2 sine u j. And the magnitude of our cross product, r sub u cross r sub v, is going to be what? 2. Now we need to express. So we found our cross product. We found the magnitude of our cross product. What's the next thing we need to do to evaluate our line integral or surface integral? Sorry. We need to change what?
Change x and y in terms of u and v.
We need to express our function in terms of our parameter. So we're going to say f of r of u and v. Express this in terms of our parameter. What is our function going to be in terms of our parameters?
2 cosine u plus 2 sine u.
2 cosine u plus 2 sine u. X is cosine u, y is sine u. Now we're ready to evaluate our integral. So we have the double integral, and 0 to pi over 2, 0 to 2 of 2 cosine u plus 2 sine u times 2. And the order I did here was dv du. Nice, easy integral to evaluate here. This evaluates to 16. One note, something that I've been seeing with evaluating integrals is that we're forgetting, especially with trig functions, that we end up with a value for our lower limit. Sometimes cosine and sine, it's always 0. And sometimes we're forgetting to subtract that lower limit. So just little careless mistakes that I'm seeing in evaluating integrals. Question, Cole?
When will we know to use like the green theorem to use the integral?
So green theorem, remember, green theorem relates a line integral to a double integral in the plane. So green theorem would be a line integral. The hint that you're going to use green theorem is you're taking the line integral around a closed curve. So that's the first clue that you might want to use green theorem.
Say like the reverse of green theorem. That's what I'm talking about later.
The reverse of green theorem is to find area. So if you're finding an area of a region in the xy plane, then you could use the reverse of green theorem. That's really the purpose of the reverse of green theorem, is to find an area. Okay? But we'll get to something similar with surface integrals, where we change from a surface integral to a line integral. That's Stokes' theorem. Or the divergence theorem will talk about a flux integral and a volume integral, or a triple integral. So there'll be some similar things that we're going to do with that. All right, guys, this is driving me crazy. All right, let's do one last example. This one's a little longer, a little more work, and there's something at the end that I want to kind of re-emphasize. What's that? So we want to evaluate this surface integral. So we're going to evaluate, now we have a function of x, y, and z. F of x, y, z is the square root of x squared plus y squared plus z squared. I'm just kind of emphasizing what this means. And our surface is z equals the square root of x squared plus y squared. And our region x minus 1 squared plus y squared is less than or equal to 1. So let's look at what we're talking about first. Just based on the function and our surface, how do you think we're going to end up evaluating these integrals? Just by the way that everything looks here, polar. We're probably going to use polar because we have these radicals in this x squared and y squared, y squared, z squared. So we're probably going to end up converting to polar coordinates. What is this surface? This is a cone. Z squared equals x squared plus y squared. That's a cone. What is this telling us?
The region of the circle with radius 1 shifted 1 unit to the right.
So our region in the xy plane is a circle in the xy plane. We're shifted 1 unit to the right. So we're evaluating the surface integral of this function over the cone above this circle in the xy plane. So if we wanted to draw a sketch of this, we'd have an idea of how to draw the sketch. We have a cone, and we're projecting that circle up onto the cone, and we're evaluating this function on that region of the cone. So this part gives us, just to emphasize this is the surface. And this part is the region in the xy plane. So this is going to give us our boundaries for our limits for our integrals.
So then the f of x, y, z is just what you're evaluating on the surface?
Right. So if we, without some kind of interpretation, we're just really saying what is the value. We're taking a little piece of the surface, multiplying that area times the value of this function on that area. So if we thought of this as a density function, density per unit area, we'd be finding the mass of that little piece of the cone. All right. So for our surface integral, what do we need to find? The partials of which function?
The main function. Alright.
All right, guys, listen up.
F of x, y, z with z substitution.
So for our ds, we need a partial with respect to x squared, partial with respect to y squared, plus 1, take the square root of that. Which of these functions are we taking the partial derivative of for that ds? S, the surface, right. The ds is a piece of the surface. So we have three choices of functions here. So we want to make sure we take the partial derivatives of the right functions to find our ds. ds is a piece of the surface, so we're dealing with the surface. So we need dz dx. dz dx equals what? 1 over x squared, 1 over square root of x squared? 2x, x, 1, x, there we go. X over the square root of x squared plus y squared. And we have kind of a symmetrical situation here. So dz dy is going to be y over the square root of x squared plus y squared. So ds, our little piece of area, is this lovely radical. And we need to simplify this. What does this simplify to? Square root of 2. So we get a common denominator, and we end up with x squared plus y squared, and this all simplifies to square root of 2. Don't you wish you could always do that in your classes? What does this simplify to? Square root of 2.
Square root of 2.
And not have to work it all out. All right, so now we have, and we've got our dy dx. There's our dy dx. Now what's our next step? F of x, y, z in terms of our parameters. So we're doing a double integral, so we can only have two variables. So we need to put our function in terms of our parameters. So f, I'm going to say f in terms of s. So we need to express f in terms of the variables on our surface. So f is going to be the square root of x squared plus y squared plus square root of x squared plus y squared squared, which comes out to what? 2x squared plus y squared. Right, 2x squared plus y squared, yes. And I'm going to write this as square root of 2 times x squared plus y squared. And now we're ready to write our integral. So I haven't even started evaluating yet. So finally, I'm going to go to the next page. So here's f in terms of the parameters of our surface. Here's ds, and we're ready to write our integral. So we have the double integral over our region in the xy plane of square root of 2 times the square root of x squared plus y squared times square root of 2 dy dx. And I'll simplify a little more. 2 square root of x squared plus y squared dy dx. All right, now we need to evaluate this double integral over our region. So R is, we said x minus 1 squared plus y squared, less than or equal to 1. So what are we going to, what did we decide earlier? We wanted to use polar coordinates. So we're going to say in polar coordinates x equals r cosine theta, y equals r sine theta. Polar coordinates are going to help. Still going to be interesting. Still going to be interesting. So here I have r cosine theta minus 1 squared plus r squared sine squared theta, and that is less than or equal to 1. So we need to simplify this. I'm going to square this out. So I get r squared cosine squared theta minus 2r cosine theta plus 1 plus r squared sine squared theta, and that's less than or equal to 1. And this simplifies, thank goodness, to r squared from the r squared cosine squared theta, r squared sine squared theta, minus 2r cosine theta, and that is less than or equal to 0. What's that? I subtracted 1 from both sides. So we're trying to find our limits on theta here, r and theta. So I'm going to factor out an r. R times r minus 2 cosine theta is less than or equal to 0. That's 1. I said 0, wrote 1. So we're going to say that r doesn't equal 0. So r equals 0 is at our origin, so we're going to ignore that part. So we have r is less than or equal to 2 cosine theta. So in polar coordinates, our region is r is less than or equal to 2 cosine theta. 2 cosine theta is this circle in polar coordinates. R equals 2 cosine theta is traced once from theta equals what to what? Think back to the chapter 14 test, that lovely last problem. R equals 2 cosine theta. If theta equals 0, r equals what? 2. If theta equals pi over 2, r equals 0. So if I draw a little sketch, I'm starting here, my circle goes to here. So I get half of it from 0 to pi over 2, the other half from 0 to pi. So this is traced once from theta equals 0 to pi. So finally, we're ready to evaluate our integral. So we did one page to get ready to evaluate our integral. We did another page to find our limits, and now we're ready to evaluate our integral. So we know that theta varies from 0 to pi, and r varies from 0 to 2 cosine theta. So we have, and here's where the interesting part comes in. 2, 0 to pi, integral from 0 to 2 cosine theta. r times r dr d theta. R dr. Too bad we don't have one more r. We have r dr r, right? So there's our integral. 2 integral 0 to pi. Now we need to evaluate this thing of r squared dr d theta. We evaluate our integral first, so we get we get 16 thirds, because we get r cubed over 3, and 2 cubed is 8, 2 is 16, 0 to pi of cosine third theta d theta. What happens when I evaluate, if I were to evaluate this as is, I would say 16 thirds, or 1/4 times 16 thirds times cosine to the 4th theta on 0 to pi. What would happen here? Oh, right, because of the chain rule. All right. My point. What is a period of cosine? 2 pi. What is a period of cosine thirds theta? If I evaluate this integral, if I leave the limits, I end up with an integral that evaluates to 0. So what do we have to do? First off, does it make sense that this integral would evaluate to 0? It does? All right. Let's go back to our original integral. Is this in this region? Is this ever negative? No. Is our surface, is this negative? No. So if we're integrating two functions, we're multiplying two functions that are always positive, can we get 0? Unless those functions were identically 0, then we have to get some kind of positive value. So if we integrated this as is, we could integrate this as is, we would end up evaluating this to 0. What's that?
You said like we should be able to tell, like what do you look at in that?
All right, so let's go through this. Cosine, the period of cosine to the third is pi.
Okay. Then that's fine.
But so let's go through this evaluation. So now we've got that sort of cleared up. How would we evaluate this? There's an easier way to integrate by parts than integration by parts. What's Garrett? We're going to split it up. So this is going to be equal to 16 thirds. This is one integration technique that we have a hard time remembering. I'm going to write this as cosine squared theta times cosine theta d theta. Right, so we get 16 thirds. The integral will go from 0 to pi, 1 minus sine squared theta, cosine theta d theta. And now we just have two easy integrals to evaluate. So this is 16 thirds times, we just have the integral of cosine theta here. So that's just sine theta minus sine theta over 3, where u is sine theta, so we have, and this is our du from our cosine theta d theta. And we're going to evaluate this on 0 to pi. So this was a part that I was kind of jumping to before, that we end up with a sine to something in our integral. So our integral has these signs in it. And if we evaluate this on 0 to pi, sine of pi is 0, sine of 0 is 0, and pi is 0. So this evaluates to 0. So what we're going to do is split it up into a portion of the period. So I'm going to say this is 2 times 16/3 times sine theta minus sine third over 3 theta, and we're going to go from 0 to pi over 2. Sine cubed theta. Yeah, that was a strange way to write it. All right. And when we evaluate this, now we can evaluate this, and we end up with 64/9. All right, wasn't that a nice problem? No?
Give that on the final.
No, the final, the problems on the final, everyone has always said that the final, the UCB final, is easier than any of our tests. And their note sheet is like a booklet.
So they give it the whole half.
Yes. I'm giving everybody the same this UCB final. That's it. Just
And the note sheet will give that to
yeah. Yeah. All right. Any questions on surface integrals? But don't you like? I really enjoy problems like this where there's much work setting it up as there is to solve it.
See, I just went